Okay, thank you. Yesterday we proved that on a simply connected compact real manifold there are no real analytic foliations of codimension 1. And some techniques was developed to prove this. And if you think about that, you might be disappointed, because after all what we proved that something does not exist. Well, something nice. It's not bad, foliation. But fortunately, this is a halfway to prove another existence theorem, theorem of Novikov. And this we shall prove today. So let me start with discussing an important notion in foliation theory, a holonomy. First of all, what is a pseudogroup? Suppose you have a manifold. A pseudogroup of diffeomorphism pseudogroup of local diffeomorphisms on M is the following object. They are given some diffeomorphism Gi from some open sets to some open sets. So Di and Ri are open in M. So some collection is given. Okay. And this collection satisfies the following axioms. First, identity of the manifold, well, which is a map from the manifold to itself, is in this pseudogroup. How I shall name it? H. It is in H, in our pseudogroup. Second, if Ji and Jj belongs to H, then composition belongs to H if it is well defined. On the open sets where it is well defined. Okay, it might be not defined, but okay. So, well, if domain of J intersects the range of I. Okay, let me be more precise. Third axiom, if G I belongs to our group, then restriction of Gi to any open V belongs to our group as well. To open V subset of corresponding Di. 4, and the last one, so you can glue them. Okay, so if you have two elements of our pseudogroup which coincide such that Gi on the intersection of Di with Dj coincides with Gj on this intersection, and so you have intersection of two Di, Dj, and you have some mappings. an image is this. Okay. And then what? Well, okay, so this is the image of this is intersection. This is its image. So we require that our diffeomorphisms coincide on this, agree on this intersection. But there is one unpleasant thing, is that this guy might intersect itself. Okay, so, oh, this is not a bad, I'm a very bad artist, okay. Okay, somehow, so the condition would be that this does not happen. So the images is in fact this. So such thing does not happen. Okay, and then the following element, which is GI on DI and J on DJ belongs to our group. So we can glue diffeomorphism. So such object is called a pseudogroup. And now in our setting, we have a pseudogroup. With every foliation, there is a connected to it pseudogroup, and it follows. The manifold is a, so if U is a covering is a cover of our manifold by flow boxes. Okay. And then if the total space, the manifold on which our pseudogroup acts, is not M, is a union of transversalities. Is a union, disjoint union of all. So this is UI of all transversalities. Just disjoint union. They do not correspond to each other in any sense. And now, what will be the diffeomorphism? Suppose you have two UI and UJ which do intersect. That what you can do? You have transversalis TI here and TJ here, and you can take point called TI, small ti. Ti is a variable on this transversalis. Took the leaf which passes through this point, and look where this leaf intersects another transversalis. And you call this the image. So Hij will be a mapping from certain part of this transversalis, Dij in Ti, to some part Rij in Tj. Be a diffeomorphism. So now you have some number of such diffeomorphisms, and then you might be able to compose some of them. For example, on this picture, you have Ti, you have some UK, and some UJ. Ti and UJ do not intersect, but nevertheless you can do the same thing. So a pseudo group generated by all these maps, all these diffeomorphisms, is called the holonomy pseudo group of the foliation. So HL, the holonomy group of L, of the foliation. So it's a group generated by Hij, by all Hij taking on intersecting flow boxes. Okay? Well, and now the following notion is a transverse measure. So this was holonomy. Second point is transverse measure. Transverse measure is a collection of measures mu I, so on Ti. So each mu I is a positive measure on the transversalis Ti. And condition is that these measures are invariant under holonomy pseudogroup. So condition is that if you take mu I and you restrict it to this Dij, where Hij is well defined, you push forward this measure. As here. Yeah, look. You have measure on the whole Ti. You restrict it to this piece, Dij. And then you have map to this Tj. And you push this measure, and condition is that this should be mu j restricted to Rij. Okay? This is it. So transverse measure is a bit an abstract thing, so it's a collection of measures. And if you have some foliated atlas, some number of transversalities, and if you have such measure, it not always exists. But if such measure exists, but then it induces a measure on any transversalis, obvious. You take any transversalis somewhere, and then you have these holonomy things, and they push, and you got a measure. Now, in fact, the measure is defined on all transversalities somehow. Okay, but, well, we don't need this. And now, starting from this measure, we can define a foliated current. So let rho I be a partition of unity, subordinate to this covering which you have. Okay.
What is Dij? The intersection?
Dij. Okay. Is this thing here. This is Dij, where holonomy is defined. Okay. It's not defined everywhere. If you go here, then you will not intersect the second flow box. So it is and then it maps this to an open set, which is a range. Okay.
So the condition is that the transverse measure works like this for flow boxes for some atlas.
Yeah.
So for like just a number of.
Just 5. Yeah.
And then you say that.
You take any flow box. You take any flow box, and you take any transversalis, and then you will got a measure on it.
Okay.
And I shall discuss this a bit in more details later on. For this I have second picture. Okay, now let we fix partition of unity, and then we shall define the following functional C on P forms. So omega is a P form on our manifold. Yeah, I forgot to say that our foliation is of the dimension P. L, dimension of L is P. Okay. And now we take a P form and we want to define some number, the value of our functional on this form omega. And we do the following thing. We take rho I omega. This is a form with compact support in UI. Yeah? Okay, let me, this is UI. Now this form has support in UI. So I can integrate it along any plug. So this is a plug. So this is a transversal salis. This is a point variable on the transversalis ti. I shall denote by small ti. Okay, and then I have projection pi, and I take pre-image of ti. Yeah, so I take this plug. And I integrate my P form along this plug. And then I integrate over the transversalis ti against measure which I have, d mu I. Okay, let me put some brackets to be correct. And then I take the sum over all. Yeah, usually finite, because we have compact manifold, you have finite number of charts, and so. So this is a number. This is a number. And so you get a linear form, linear functional, on the space of forms. This functional is continuous in the natural topology of forms, and such thing is called a current. So this is a current of dimension P. It acts on P forms. So current, more or less, every current, more or less, in some sense, is of dimension P, is the integration of forms along p-dimensional submanifolds. Well, it's not true what I said, but somehow. It's a limit of such things. Okay.
Depends on the partition of unity. It depends on the rule.
Yes. The definition looks to depend on partition of unity. And therefore, I will give you an exercise. Which is solved in my notes. And it says that it does not depend on the partition of unity. And moreover, so how you can prove this? You just prove that for a form with compact support in some chart, this thing does not depend on the partition of unity. And that's enough. Okay? And the claim is the following. If the support of your form is in chart, okay, say uj is compact, then your current acts as follows. It's just an integral over the transversalis Tj of over pj minus 1 of tj omega. You integrate, and then you integrate against this measure. So there is no partition of unity here. So if your form has support in the flow box, uj, then this current acts in a natural way. You integrate along leaves your form, and then you integrate with respect to the measure you have on the transversalis. Okay? And this, now C is called a foliated, not just a current, but a foliated current. Associated with the transverse measurement. Yeah, transverse measure often will be denoted as mu. So with each measure, transverse measure, you can associate a functional on P forms, which is somehow integration. Okay? And then I don't want to say all this. Yes. And now, no. Now let us give an example. Let us see an example. Suppose we have a compact leaf. So suppose L0, Lx0 is a compact leaf of our foliation. Okay? So passing through point x0. Okay? Now, take a transversalis T0 through this point. And define mu0 to be a Dirac measure at x0. Okay? So I need to define a measure on a collection of transversalises. I started with one. Okay? And now for any other, okay, this was flow box, say U0. For any other flow box, UI, and transversalis Ti, I take a point xi of intersection of this transversalis with my compact leaf. So if I took this foliated covering small enough, fine enough, there will be only one point. And I defined mu I is a delta measure of xi. Okay, now this is obviously a transverse measure. Okay, this is a transverse measure. Now, what meaning it has? Let C be the corresponding foliated current. Let us compute C, value of C on any P form. So we write it is a sum. Yes, I forgot to say. This defines you transverse measure on transversalises which cut our leaf. On all others, it's 0. Okay? Now, it will be, according to our definition, it will be the sum of the integrals rho I omega along pi minus 1 of xi. Why? Because it should be variable ti and then integration over ti. But again, the delta measure centered on xi. Now there is only one thing. And then this is the sum over all ui which intersect our leaf. Now what we do, look, we have a flow box. Well, T0 is among the flow boxes. And we restricted our form, and this piece is a plug, is a leaf. So in fact we are integrating, this is the integral of rho I omega over the leaf. Okay? This is a form with compact support which is contained here. And so it is a globally defined form on L. And this integral is just integral L. And then we need to take sum of I. And now we use rho I as a partition of unity. So this equal to the integral over the leaf of our form. So our current is a current of integration. It takes a P form and integrates it over our compact leaf in this example. Okay. And now, so what is that? And now there is an important statement that okay. So using transverse measure, we constructed a foliated current. In a second, we shall prove that this current is closed. And the theorem is that this definition, okay, star, this formula, star, establishes a one-to-one correspondence between transverse measures and closed foliated currents. And closed foliated currents. Well, I'm not going to prove this in both directions, but I will prove that this current is closed. Okay? So I have a transverse measure. I have constructed a current, and I want to prove that this current is closed. So
What does it mean?
now I'm going to tell you what does it mean. So differential of the current is a dimension p minus 1 current. And it acts on forms. Now alpha is now p minus 1 form. As follows. This is a definition of the differential. This is a action of C on d alpha. but with some sign. Sign, well, it's not important, minus 1 to the power q plus 1, if I'm not mistaken. Q is n minus p. Okay. Okay, anyway, some sign here. And this, well, and we want to prove that this is 0 for every alpha. We want to prove this is 0. So, no, we write the same thing. We write sum over I, C, partition of unity d alpha. I did nothing because sum of rho I is 1. Okay. Now I want to say that this is the same as, so how to say this rapidly, is the same as C over d rho I alpha. Okay, why is that? It's not maybe immediate, because in fact there are something else here, minus what? C and differential of rho I alpha. Okay, now this is true. Yes, differential of rho alpha is rho alpha d alpha plus d rho I d alpha plus d rho I alpha, yes? Okay. And now this sum is what? Is a C acting on the sum of d rho I alpha. The sum of d rho I sum is the differential of 1. So this is 0. So I have only this thing. And now I must apply my definition. So I must integrate. Should I apply? Yeah, okay. I must integrate. And I want to use this thing, exercise. Yes. According to my exercise, if my form has support in UI, as it is the case, my functional on this form is just integral over Ti of the integral of the Pi minus 1 of Ti of this form, which is in my case d rho I alpha, and an integral against measure and sum over I. Okay? But now we are integrating over open set differential of the form with finite support, with compact support. So it's 0 by Stokes theorem. Okay? Hmm?
Do we have for every integration current, for every current of integration is closed?
Is what?
Do we have the following? Every current of integration
Yeah.
is closed.
Is what?
Closed.
No. No, no, no. No, look, I don't want to discuss this, but maybe I have no time to finish today anyway. So better I say something. Now look, what is the form of all currents directed by our foliation? So we have some special currents, so associated to transverse measures. We prove that the currents are closed, and would we spend 1 hour more, we would prove that if you have a closed current directed by L, then there is a transverse measure which corresponds to it. Okay. We are not going to prove it, but in general, you fix a P vector field tangent to the foliation. What is that? Locally is this thing. Locally is V1 of x wedge V2 of x wedge Vp of x, and this is the following thing. You have a leaf which passes through point x, and V1, V2, Vp is a basis. Okay? Is a positively oriented basis. Okay? So locally is this. But you can define it globally because our foliation is orientable. There is a global P vector field. I just explained you what is P vector. And P vector field is a P vector at every point, smoothly depending on x. Okay? And now, what you can do, you can, if you have a form, if you have a P form, you can evaluate what is P form. P form is a linear functional on P vectors. So you can evaluate it on this guy at point x, and then you can integrate this over manifold M against any Borel measure. Borel measure means that measurable sets are Borel sets, not all the back measures. And this will be a current. This will be a current. So current which is defined by two things, by P vector field, which is tangent to the foliation. That's why we say that current is directed by the foliation. And there are some measure. It can be delta measure. Okay. And our current is more or less like that, but a little bit different. And this current, it might not be closed. There is no reason for this current to be closed. Okay. Well, so we had today two important notions, holonomy and foliated currents, and transverse measures. Okay, three important notions. And now, what I want, and now, okay, I must erase something. Oh, okay, I'm going to erase this. And now, suppose N is a submanifold of N which is transverse to our foliation. So dimension of N is Q, which is N minus P. Okay. So like on this picture, you have, it is disconnected here, but you should understand that it goes somewhere and goes back. Okay. So manifold N, which transversely intersects all leaves of our foliation. Suppose you have such. We know that we can construct transverse curves. So we have such examples. Okay. Now suppose we have, and then I want to explain you that a transverse measure induces the usual measure on this submanifold. Well, first of all, what is doing a holonomy group? Now look on, I'm not going to write too much. Now let me take a flow box UI. In this flow box I have a transversalis Ti. and as well my manifold intersects this flow box in this way. So if I take this cover sufficiently fine, this will be the picture. And now what I can do, I can project n, this piece on n, to the transversalis, pi. Okay. Then I can apply holonomy and send it to another transversalis, somewhere where I can. And then I can do the inverse. From this transversalis, go back to the manifold. So I obtain a local diffeomorphism on this manifold N. In fact, we obtain a group of local pseudo group of local diffeomorphisms of the transversal manifold. A holonomy group induces a group of local diffeomorphisms. And if we had a transverse measure, but then I can push this measure. I can take pi and push down measure mu I and got a measure, I'm sorry, I took inverse. Okay. I take inverse diffeomorphism pi from Ti to this piece of manifold, and I push measure, and I get a measure on this piece of manifold. And the same I can make here, measure. And this measure, this collection of measures, is invariant under this pseudo group of diffeomorphisms. And then it defines a measure on the whole manifold. So we can, from the transverse measure, we can produce a usual measure on the manifold, on N. Okay. And now, lemma. This lemma I'm not going to prove. It's proved in my lecture notes. If, in the conditions as above, if N intersects the support of a transverse measure, of some transverse measure. So suppose it exists, and our transverse manifold intersects supports of mu, then the homology class of N is not zero in the corresponding homology group. So N is not a boundary. N is not a boundary of manifold of dimension q plus 1. What is support of transverse measure? I forgot to say. So we define transverse measure starting from transversalities, yes? And this is a mu I. It has some support, yes? If some leaf intersects the point of support, then we say that all this leaf is contained in the support of transverse measure. So support of the transverse measure is a collection of leaves which somewhere intersect transversalities where measures are not zero. Okay? Now, well, I'm not going to prove this. Okay. Better I shall start with vanishing cycles. So we developed some machinery and some analytic machinery, And now we are going back to geometry. So we have a foliation of dimension of codimension 1 on a manifold M. I always suppose that it is compact and everything is orientable. So, definition: an embedded closed curve gamma from the unit circle to some leaf L0. So I let L0 be some leaf, not necessarily compact. Okay. So an embedded curve in the leaf is called a vanishing cycle. A vanishing cycle if there exists a homotopy of curves, each to its leaf, so you can deform this. Of course, gamma 0 is gamma. Gamma 0 is gamma. Such that, first, for all t not 0, so not for gamma 0, gamma t of S is homotopic to 0 in the leaf. For an embedded curve to be a homotopic to 0 means it bounds a disk. But gamma 0 is not homotopic to 0 in L0. Well, let me give an example. Consider a solid torus in R3, usual torus. And the foliation will be the following. The surface of the torus will be a leaf. It will be L0. And all other leaves are like that. And so on. Okay? Now, this is a foliation on a three-dimensional manifold with boundary. But I don't want to discuss this too much, but you can take two copies of this and identify surface toruses. And you will get a compact three-dimensional manifold with foliation, having this torus a compact leaf, and this manifold is a three-dimensional sphere. Okay? But, well, I don't need to discuss it. And now, vanishing cycle. If you take a circle here, gamma 0, it is not homotopic to 0 on its leaf. But closed, but you can perturb this thing and get to the nearby leaf, and this is homotopic to 0. Okay? lemma lemma 2 let L be a codimension 1 foliation on a compact, simply connected manifold M. Then L possesses a vanishing circle. Okay, now let me briefly explain the proof. So, before telling you the proof, I want to tell you our aim, which will be finished tomorrow. Today, probably not. We are going to prove the theorem of Novikov, which says that if you have a codimension 1 foliation on the three-dimensional sphere, so dimension 3, codimension 1, then foliation by surfaces, then this foliation has a compact leaf, always. And the first step is to find a vanishing circle. So why is that? So if we have this foliation, then when we proved the theorem of I cannot pronounce this name, Haefliger. There is no N here. Haefliger. Okay. I don't know. Well, so when we proved this theorem, so what we did, we started from the transverse curve to our foliation. Then, since manifold is simply connected, we make homotopy to 0. Therefore, we obtained a map from the unit disk to our manifold. Then we put this map in general position, J. So from the disk to our manifold, which has these nice properties, which I don't want to repeat. And then we considered the pullback of our foliation on the disk. So roughly speaking, the leaves of this foliation are intersections of disk, of the image of the disk, with the leaves of foliation L. Okay? And we introduced the set of polycycles which are either limit polycycles or infinite intersections of limit polycycles. And we prove that this set contains a minimal element. So let gamma be this minimal element. Minimal. You see, I'm using everything from this theorem, more or less. So I took this, and now I will make a few simplifying assumptions to make this quicker. I suppose that this gamma is a smooth orbit, not something like that. Okay? And now we proved in the exercise yesterday that it contains equilibrium points necessarily. Every polycycle, every cycle contains these equilibrium points. And now we can compute, and here our vector field, which generates F, is tangent to this circle. And therefore, its index of the vector field which is generating our foliation, index along gamma is, well, it rotates, so it's -1, I think. And now you can, and in equilibrium points are either focuses or saddle points. Index around focus, index of around focus is again -1, and index around saddle point is 1. You can prove this easily. And the sum of indices over focal and saddle points is index on the boundary, so it's -1. So focuses are more than saddles. So in second simplifying assumption will be that we have only one focus and no saddles. Okay? So our foliation is like that. Locally, you can find place where it is like that, but it is more complicated. And now, what does that mean? If you remember that this is a disk, well, a piece of our disk which is mapped to our manifold, and these are intersection with leaves. Now so there is a leaf which is just tangent here, and then it starts to cut. Yeah? So you go like that. All these curves, well, all these curves are obviously homotopic to 0. If I take this small curve, it will be homotopic to 0 in its leaf. Okay? It's just a small circle which is the formation of a point. So all these images of circles as T, this will be gamma T, are homotopic to 0. So now for T bigger than 0 and less than 1. But when we arrive to 1, it cannot be homotopic to 0, because would this thing be homotopic to 0, then again our map exists in a bigger disk. And then you can move it, push a little bit, and get circles nearby. But we know, we proved that the holonomy, when we proved Haefliger theorem, we proved that holonomy here is identity and here is not identity. And so this cannot be the case. So therefore we got a vanishing cycle in our foliation on a simply connected manifold and foliation of codimension 1.
But here it's analytic
No.
in the theorem of Haefliger.
No. The theorem says that a real analytic does not exist. Our foliation is smooth, and I gave an example of a smooth foliation which exists. Okay? But the reasoning is parallel. Okay? So it left to us almost one step, and this will be done tomorrow.